This is a loop of wire in a magnetic field. This is a demo. If you want to look at it yourself on your device or whatever, there's a guy by the name of Walter Fend. Fendit. And I've never met him, but I'm very thankful to him because he makes some great animations. And he made this one. So this is a magnet. The blue lines are the magnetic field. So which is north, top or bottom? The top is the north. Right? So this is N and this is south down here. By the way, think of the Earth. If the Earth was a magnet, which side would be the North Pole? No. Actually, the South Pole is a North Pole. So think about this. If I put a compass right here, which way would it point? It would go... Would it?
Yes.
Yeah, that's right. Your compass points because it's north, right? So north is attracted to south, yes? So if you had a compass, it would point to the South Pole because north is attracted to south and south is attracted to north, so this would be south and north. If you have a compass on Earth, where does it point toward? It points to the North Pole, right? But that's because our geographic North Pole is a magnetic South Pole. And so our compass points north to the mountains because north is attracted to south. So the Earth is...
So how do west and east work?
Say it again?
How do east and west work?
Oh, we just say that if you're looking north, west is to the left.
Okay.
And the Earth moves to the east. By the way, did you know that hold up your pen again. Go like this. Imagine this is the Earth. We'll flip it around. So this is south. Imagine this is the magnet inside the Earth. What do you think it's doing? Yeah, it's, first of all, it's tilted over. So tilt it a bit. And as the Earth rotates, it goes like this. So every day, there's a circle. The magnetic North Pole actually moves in a little circle every day. And it's actually moving. In my lifetime, it's moved a lot. The magnetic inclination used to be, I think, 21, and now it's 23 or 24. And every 50,000 years, it flips over, upside down. Do you want to know how we know that? Because if you go down to the ocean floor, you know, okay, who's a geo kid? Uh-huh.
We're not here tomorrow because we're all geo kids.
Oh yeah, lucky you. Good to be a geo kid. If you're a geo kid, you know there's these trenches in the ocean, right? Hopefully you know this. What happens in the middle trench in the ocean?
Bumps.
Not bumps. What kind of bumps? The molten hot magma comes up from under the crust, and in the middle of the ocean it goes, and it bubbles up. There's this like seam in the ocean, like a zipper almost. It's like, and the molten hot magma comes up and it solidifies in the ocean water, right?
Yeah.
I know it's bad when Colin goes like this. I've reached the limit of Colin's patience. The mid-ocean trench opens up and that rock comes up. Now it's liquid, right?
Yeah.
So when it's liquid, what are all the magnetic dipoles going to do?
They're not magnetic.
They are magnetic. Yeah, sure. It's gonna flip like this, right? They're gonna flip in line. And as it cools, they're gonna cool in place, right? Now, over time, if you stretch out from that mid-Atlantic ridge, you see, yeah, everything's lined up north, everything's lined up north. And then if you get away from the trench, all of a sudden it goes, and they're all pointing south. And there's these, if you look at the ocean floor, there's these stripes of pointing north, pointing south, pointing north, pointing south, pointing north, pointing south. And we age those rocks and we figure it's about 50,000 years to between when the magnet flips. That has nothing to do with what you need to know. Although, while I'm going aside, here's the SpaceX question. Did I tell you this already? If you ever get interviewed for SpaceX, they're gonna ask you a question in the interview. This is what it is. If you are on the Earth, do you? You walk south 1 kilometer, you walk west 1 kilometer, you walk north 1 kilometer. South, west, north, but you end up back at the same place. North Pole is number 1. Because if you walk south, and then west, and then north, you're gonna end up at the North Pole, right?
No, there's only one.
No, there's 2. Yes, there is. Well, I thought you knew. You said you knew the answer. Hey, we stumped Jeffrey. You got about 2 minutes to figure it out. Otherwise, you don't get the job at SpaceX. You know?
Is it because the Earth's round? Isn't that what it is?
It has to do with the Earth being round, yes.
You go like, and it's like you got the thing, but then it's like a.
So that's the North Pole. But where's the other
You can
place?
do it anyway, can't you?
No.
No.
If you do it here, you'll end up in, like, over there, a kilometer away. Nobody knows? I will tell you. Remind me about the end, and I'll tell you the answer.
No.
I have to make you think for a bit. Okay. Enough of that. But I will tell you the answer at the end. Okay. This is a loop of wire. Okay. And we are going to rotate that loop of wire. We're going to do what we should have done at the Physics Olympics, and we're going to hand crank it. And we're going to move this coil of wire through the magnetic field. So if there's no current in the wire to begin with, you just have a bunch of charge in the wire, right? You got positive charges, you got negative charges. And as the loop rotates, it's rotating like this. The top of the loop, this black arrow kind of shows the direction. I'm trying to, how do I get rid of this, like, all this other doodad stuff up here? Can I?
Press Alt.
Alt?
Just to happen. No.
Yes.
Never mind.
Just disable
That works on
the
Firefox. F11.
Press what?
Just press right. Right key on the right here.
Right key, like this one?
So just do control right click and then just disable the last one.
Turn off show button.
Thanks, Colin.
I think if you press F11, it goes full screen.
Oh yeah? I'll try it. F11. Oh, F11.
No?
Oh boy, oh boy. Oh, we're opening teams!
No!
Stop it. FN F11. Oh, we
Hey!
did it! Together we will prosper.
How many physics kids does it take to use a computer?
Yeah.
I couldn't even.
Hey, how many hipsters does it take to change a light bulb?
Is this relevant to the.
It's an obscure number. You wouldn't know it. You'll get that joke when you're older. And you have hipster friends who are just too cool for
On the
themselves.
recording.
Okay, this is the loop. The black arrows are the direction of the loop. So we're going to crank the crank, and we're going to crank it this way. So the top of the loop is coming kind of out of the page towards us, and the bottom of the loop is going into the page towards us. Okay, so remember the first version of the right-hand rule?
Yes.
How do you hold your hand? Show me. Like this, right? Just right angles. What's the fingers? Field, magnetic field. What's the thumb? Current, so positive charge, movement. What's this?
Force.
This is force. Okay, so if you're moving your positive charges out of the screen and your field is down, which way will they be pushed? See a lot of good hand movement. So our field has to be down. We're pushing our charge out of the screen. So they're going to be pushed, which way? This way, right? That's why there's a red arrow here. Now, if this loop is sitting still, is that going to happen? No. When you turn the crank, will you feel resistance? Like, let's say I pull the magnet out and you're spinning and you're like do do do, and then I push the magnet in.
Yeah.
You will feel it go, and you'll have to push against it, right? Why?
Because of that force.
Because of that force. Because you're actually pushing the current now through the loop. Yes, Kenta.
But if the force is this way, won't the coil try to go into the current?
That's HL stuff. That's induction.
But we have to know
But
that.
then where's the?
Yeah, we will.
But if the
The
force
angel
is that way, why is it moving or spinning?
Okay, say that again.
If the force is going towards the crank,
Yeah.
why is it spinning?
What do you mean? Why is it spinning?
Where's
You're spinning it. You're providing the force of spin. Yeah. No, you're getting ahead, but I'll get there. So this is going to push this way. Okay, but now look at the bottom of the wire, the bottom wire in the loop, and decide which way those charges will be pushed. Fingers down, right? But the charge is now being pushed kind of into the board. So they're going to be pushed this way, right?
Wait,
what?
Is that current or electrons?
You're right handed.
Let me play it so you can see what's going on.
You can only use your right hand.
Yeah, for current, you can only use your right hand. This is moving, right? So notice what's happening to the direction of current in the loop. The red arrows. Every time it turns around, what happens to the direction? It swaps, right? Because your charges at the top are moving out of the screen, but at the bottom, they're moving into the screen, being pushed this way. So top of the screen, as this one comes up, they're moving out of the screen, being pulled this way. But at the bottom of the screen, they're being pulled in, being pushed left. So top is being pushed to the right, bottom is being pushed to the left. But that's kind of cool because we have a loop, right? So everything's gonna go in the loop this way, and then the other way. Now, this was a real problem, right? In the beginning, because you get this, we wanted direct current. And so, and this is producing what kind of current? This is producing alternating current. It pushes the current out and then pulls it back, and then pushes it forward and pulls it back. And we didn't know how to deal with that in the day. So we put something on the crank called a commutator. So let me click that. And so what a commutator is, it's kind of a split. So the loop is in this thing here, but it attaches, these little doodads are not attached. They just slide on the commutator. And the black part is insulative. It's not conducting anything. And so as this spins around, you end up getting the same direction of current every time. This is a generator. This is how we generate electricity. If you have no commutator, you're gonna get alternating current. If you do have a commutator, you're gonna get direct current. But it's kind of gonna go from 0 up and then back to 0 and up and back to 0. Any way you know of to smooth out that bump? Jeffrey? If you put a capacitor in there, it will store the charge for a bit and then release it in the circuit and store it and release it and store it and release it. Like that championship team did with their solar powered car. We should have done it too. Let me just pause it here for a second. I'll take the commutator out. So just have a look at the wave at the top. So you can see that little dot. And I encourage you to play with this on your own and try to explain it to yourself or to someone else. And watch this blue dot as it goes, and you can see the current in the loop forming and leaving. Right here at the line, what is the current in the loop? 0. You're not getting anything, right? Okay, now switch this around. Oops. I know, I'm sorry I'm boring you. It's like the class before spring break. Imagine now that this is no longer a generator. Instead of hand cranking, we're like, I don't want to crank it anymore. Just plug it in. And let's say we put current into the loop. Okay. We don't want to spin it anymore. We just supply electricity. What's going to happen to the loop if we supply the electricity? It's going to spin. That's right. Turn to the person beside you and explain to them why, if we put current through the loop, it will spin. Anika, you explain it to him.
If it starts here,
Don't we need that for this?
Yes, you would need it to keep going.
This setup would go like this.
Yeah, it would. Well, no, it would just go, and then it would stop.
No, because it would have momentum.
That was timed properly, then it would spin.
It would have momentum, so it doesn't go forward.
Yeah, eventually it would get stuck, I think, though. Let's put the commutator in.
That is such a...
Okay, everybody stop. If you put current in... Oh, just when I close the door. Can someone let Allison in? The loop is sitting still, okay? And you just go, I put current in. So I plug it into some power source. Can you close the door? And we have a plus here and a minus here. And our current is going around the loop like that. Show me with your hand what's going to push this bottom bar of the loop. So you're in a field downwards, right? But now you're pushing current this way, right? So which way is this piece of the loop going to go up? Yeah, it's going to be pushed out towards us, right? So as Luke says, it'll spin like that, right? What about the top? Which way is the top going to be pushed? The current's going to be going this way, so it's going to be pushed into the board, right? So at the bottom, we're pushing the current. We're pushing the current this way. It's going to be pulled out, and at the top, we're pushing the charges that way, our current that way. It's going to be pushed into the board. And so, what's going to happen to the loop? Put your fingers like this. Which way is it going to go? And it's going to start spinning, right? This is a motor. That's how motors work.
Does the amount of current affect how fast it spins?
Yes. More current, more force, more faster spin. Can we shut the door? I told you about Michael Faraday, yes?
Yeah.
Michael Faraday? Remember that story? He gets whacked. Michael Faraday had the idea of fields. And he was kind of ridiculed. And people thought he was crazy. And then Maxwell did some equations and said, oh snap, these fields are mathematically possible. And Faraday had a problem. He knew. So there was this guy by the name of Ørsted. Danish guy. And he was giving a lecture on electricity and on magnetism. And he had some compasses on his table. And he had some electrical equipment. And he had a wire. What? Say that again? Wait, really fast. He had a wire with current going through it, and he passed it over the compass. And just by accident, he noticed, oh, what? It's moving. And he was like, electricity and magnetism, they're connected. WTF. And everybody thought, wow, that's crazy esoteric. Michael Faraday heard this, and he was like, oh, the world will never be the same again. This is how we get motion out of electricity. He worked on it for a long time, and he got a rod in a pool of mercury to spin. And he was like, boom, we did it. And he showed everybody, and they were like, meh. And then he was like, we can make this move. And he developed the very first motor. It looked kind of like what those ones that Luke was working on that I have with the 2-bar magnets. But you can make it spin. Very, very likely you have never lived a day in your life without using that concept. You have used it today for sure. So lots of big effect. One last question to leave you with.
The interview question.
Oh yeah. If I'm putting current in through the loop and the loop moves, then we have a moving loop, right?
Wow.
Which is going to do what? It's going to induce current in the loop. In the same direction or opposite direction? Opposite direction. That's called induction, and we'll learn that in the HL a little bit more. The last, should I tell you the answer?
Yes.
Please tell me.
If you start at the South Pole and you walk out to a point where the circumference around the pole is 1 kilometer, and you go 1 kilometer up, you can go down, walk the circumference in the western direction, and walk back up. And that'll get you your job at SpaceX. Have a great day, everybody.